regular names so you can understand what's going on. The node list has a list of the VO servers. Here's the two VO servers I'm using in here. The disk list, you include this extra commands, the disks that are making up your shared storage pools. So these disk names are actually matching what you are doing there. And they actually produce this command that produces this output in here. And this is the format visualize this vector bit bold in here. And as you hear this my B7000s, and you can actually see the same number in here, so you can make sure that you want the right low. And here's my low Stella, and here's the two disks of it. So once you've created a node list and the disk list command, you're ready to bring it back to shared storage pool. The next thing you're going to do then is run this customize command. This is going to take the backup file, and then it's going to have a list of the host names and a list of the disks that you want to prepare. So in this case, this is my backup file here, my Stella pool, my variables and my disk list, and it asks you, do you also want to do all the early mappings? Yes or no? Return yes, and then writes lots of information on the screen. Don't worry, you have to read or understand what's going on. If you say no, it builds the shared storage pool, and then there's you to run the LU-map command to connect the new virtual disk to the new virtual machines. Of course, the first time you want to do this, you just use the no option. Let's just get the shared storage pool up and available. Perhaps if you're testing it, then you want to start doing the mapping. So next time you run the DR test, you'll select yes and try using the map file. In my case, I typed in no, and it says this new configuration file is created successfully. It hasn't actually recovered anything at all now. It just has this new backup command that has the right VO servers in it and the right LUN IDs in it. So when we recover it, we will actually grab this new copy of the pool. So here's the actual restore command that does the hard work. We've got the same as the original name for the pool in here, Stella. This is the new repository disk that we cleaned earlier on. Here's the new fixed backup, and we're going to ask it to do an operational type cluster remote. This is the new thing that's been added with the fix. When it actually does that operation, you actually get on the screen something that looks like this on the screen. I was rather confused here, but because it's worked fine, then it doesn't actually output any list of devices in these headers. And this is a good sign. This is, as you can see at the top of here, it says restored successful. This is a good sign. You get this empty header files coming out. That command will take just a couple of minutes in my very slow example here, and then you get this sort of thing. Well, what do I do next? Well, you actually have the pool created, and the cluster is up. So the standard cluster list will tell me the name of the cluster, Stella, and then we can use the status command. You can see the two VIO servers are running here. If we list them, we find all the logical units are here and ready to go. Everything is mapped in this case because we hit no option to not do the mapping for the virtual machine. So it's all operational and ready to go. Sigh of relief at this point that we've actually done the covering and it looks fine. Now let's rewind. If we took the Y option to do the mapping, you then get the list for do you want to map all of them, and select the virtual units or no X. And if you go for the 1 or 2, then you need to supply a mapping file. File looks like this. So you have a host name type in here. Then we have the VIO server that is on the source, and the VIO server that you now want to use on the target machines. Then we have these codes for the source location code and the target location code. Just got a more worked example that hopefully you can understand what's going on. But you have one of these for each of the VO servers that you used to have, mapping it to the VO server that you want now, and then the mapping of the location code. So here's my little worked example. Now VO server 1 is what it was called. It's now called DR VO server 1. And this location code in here is the vhost adapter location code, or virtual SCSI location code, that is connected to the virtual machine. So knowing which vhost you had in your source site and now your target site, it will connect all the logical units that were connected to this vhost to the new vhost, and so the new virtual machine that you created at your disaster recovery site. Sounds very complicated, actually fairly simple as long as you have the information. This is the output, if you like, from the ls-map -all command, so worth saving that as well as the backup. So we lost our primary site and we recovered everything onto our disaster recovery site. It's all working nicely. Fixed repository disk, all the virtual machines we connected and started up, and we're working fine. Excellent, well done. Now, however, you recover your source or primary site, and what happens when you do that? Well, not much, because you actually have different disks in this situation, so they're not going to corrupt each other's file systems and that sort of thing. If you haven't changed the IP addresses, then you'll actually have two machines with the same IP address if you bring up your original virtual machines, and that could cause a lot of problems, so be aware of that. But we now have, if you like, the good disks down here on the DR site. Maybe you want to move these back to our original site, which you could operate at your DR site until you have another disaster and treat your original as your new DR site. But if you want to go back, what are the options? Well, I can think of two ways of doing that. One is that you remove your shared storage pool data up in here, maybe just write zeros all over those LUNs, for example. You can actually keep the LUNs, but we want to overwrite them. Then we stop all our virtual machines down in here, stop all the services that we're supplying, so that's going to create a complete outage of everything using the pool. And then we do a reverse DR recovery, so we'll actually do a DR recovery back to our original site, do the recovery again, and then bring up everything on our new site, making sure that we never start the DR site with those disks. The second option, if we only restarted a few virtual machines on our disaster recovery site in here, maybe the blue one is a test dev type system, so we need to recover that. And we use the green one in here, perhaps it's the prime application or database or website or something, and so we were running this in disaster recovery mode. What we need to do then is only copy the logical unit that this virtual machine was using, logical units. So if we stop this virtual machine, then we use DD to copy these out, FTP these over to our original site, and then we can DD these back into the original logical unit. Then we've freshened up the data in our original shared storage pool, and we can start the green service back up in here. Want to make sure we'd never restart this guy here, of course, because that would cause confusion. If our logical units were thin provisioned, of course, this would have made them thick provisioned by the time we copied them back over here, because the DD will copy out all of the unused logical unit blocks as a pages full of zeros. And that's it. It's disaster recovery. In my small case in here, it took a few minutes, so a larger one may take a bit longer to do all those connections, but pretty simple to do once you've got yourself prepared. It's at your own risk, but at least we do have real disaster recovery, and we can practice it in advance. You need to test it to make sure that you are ready on your particular equipment and it works for you. Decide whether you want to do the manual or the scripted mappings, and prepare for that. But make a note that it's not like full power HA. We don't have failover and failback capability. The failback is a bit more complicated, and you have to have a plan to do that. Hello, my name is Nigel Griffiths, I work in IBM Power Systems Advanced Technology Support in Europe. In this video, we'll be using a Power 8 machine and looking at how we can get hold of the temperature of the air coming in the machine and coming out of the back in centigrade, and we're looking at the electrical use, the wattage being used by the computer. Now, if you want to do this, there's two important documents you need to get on the energy scale for the Power 8 systems, and then the more detailed with a few worked examples. This was very helpful in getting going, and I thank the providers of that. I couldn't find it, so I had to go and ask the developers, and there it was. Now, don't worry about these URLs, the standard IBM website names from hell. I'll put these on the YouTube page for my movie, and you can collect them from there. I'll probably make an expert blog as well. Hopefully you can find that too. So here's the outline of what you have to do. You need a special tool to read a SIM database. I've come across these in the past. They're fairly ghastly, to be honest. The best bet is to use this thing called a WBEM-CLI. No idea how you meant to pronounce that. There we go. This is available for Linux as open source, and you can run it on Windows, but come on guys, us power guys are hardly likely to do that, are we? Right, now use this command once you've got it installed on your Linux system, and you can use Linux on Power for this, of course. Then you need a magic incantation of options to actually get this to work, and I defy anybody to read the manual page and work that out. And it's actually going to then go off and talk to the Power 8 service processor, the FSP, and get the data. Now the return data comes back in a right old mess, fairly ugly format. You actually get the previous 120 minutes at 30-second intervals, so that's 240 pieces of information. And then you have to reformat that, unpick it, save it, however you want to do that, and graph it in some tool of your choice. Now, unfortunately, I don't know of any tool that will actually do that at the moment. So we're going to demo all of the rest of this. We're going to install that CLI program on Ubuntu on Power. Now that comes with a little bug. At the end it seems to corner, but we actually get all the data out of it, so that's okay. I tried running this under SUSE 11.3 on Power 8. That worked fine, so it's a little bug in the Ubuntu version. Then we'll explain the magic incantations of what you have to put where to get this to work. There's more information of that in the documentation if you want to try other permutations. And there is some other data that you can get, for example, what performance and power saving mode the actual processors are in. Then we're going to fetch the data for temperature and the watts of electricity use, and then we'll have to look at what comes back to actually unpick it to find out where the information is, and they times the numbers all by 100 just to make it really difficult. Then we're going to show you some graphs that I generated before and during a benchmark, so we can see the actual numbers change as we did something on the machine. Right, I'm here on my Ubuntu 14.10 on my Power machine. We look in etc star ease, we'll pick up anything ending with release regardless of the upper or lowercase, and we can see Ubuntu 14.4 doesn't tell us anything about the processor in here at all, but with another command to do it, and it's CPU, and that tells us little endian. No, that's nice and clear. We have 16 CPUs, well they're actually what Power guys would call a logical CPU or SMT thread. Threads per core 8, yep, so we've got 2 CPUs in here. Unfortunately this is all wrong in here. Cores per socket, no, I think that's about 4 on this model. And we have 2 Power 8 chips in each socket. But we do have 2 sockets in the machine, not in the cell bar, of course. This is IBM Gobbledygook for an S824 model of machine, and some internals here. Okay, clear the screen. I'm actually running as root, as I did a sudo space bash, so that I don't really want to type sudo for the rest of my life, and I'm quite happy being a root user. I've had 35 years experience of that. Okay, so let's do our install now. So we can just do an apt get install, and I want the WBEM software. Not quite sure what it's called. I think it's got CLI on the end of that. We can let it find it, and we'll scroll back a bit in here. What's it found for us? Here we are. Yep, it is CLI. That's the package it's going for. Quite a long list of dependencies, and unfortunately we can just type return. The Y here is the capital, so that's the default. So let's just install that.
the screen. Let's see if we got the WBEMCLI program available to us. Yes, we have. Excellent. Oh, yeah, the screen. Okay, so I've created a file here called X. Not very original. Needs to be something more sensible, but it's nice and short. And here's my WBEM CLI command. Not sure how you actually meant to sort of say this little thing. And we've got an NL in here, so it'll throw some new line characters into the output, so it's more readable on the screen. You probably want to skip that one if you're taking the output and parsing it through said grep org or something to make it look better. No verify means don't go checking my certificates, because that ain't going to work. That seems to work fine without that. So we can switch that off. If you don't have that there, it'll just fail saying I don't know who you are. This is the actual command, the WBEM CLI command. You can look it up in the manual page what that means. Not very user friendly. And then we give it this fake URL in here. So it's secured. This HMC is the HMC user on the service processor. The IP addresses here is the service processor IP address. Now I haven't worked out how to get from your external LAN through your HMC out to the private LAN on your service processor, which is the normal way of doing things. Fortunately I have one service processor that's actually on the external network, and here is my IP address. This thing in here is the password for the HMC user on the service processor. Now typically when you connect your machine to the HMC, you have to give it a whole set of passwords. Well, the HMC one is one of those. Now fortunately, if you forget what the HMC password is, don't worry, because by accident I tried putting something else in here, and it worked fine, so it doesn't actually check the password at all. A bit worrying. Okay, now the next thing in here is the port number. This is the Open Pegasus port number, if you're looking for that on your HMC to allow these packets through your firewalls and things. Then there's some sort of hieroglyphics in here. I don't know what a FIPS is, but this is the data that we want to fetch out of our service processor. So we're now just going to run this command and see what we get back. So it's just a straight file, so it was bash, stick the file into the as the input. Now you do have to be quite patient here. It's going to take, I don't know what it is, 20 seconds or so to actually come back with some data. And it will just zoom off up the screen, and then we'll have to scroll back to see what's actually going on. There we go. Right. I'm on Ubuntu in here. The command actually ends with a segmentation fault, which is a bit of a shame. But fortunately, it's given us all the data. Now, if we look through this, that NL parameter in here is giving us all these new lines. Otherwise, all of this would come out as just one block on one line. So we can see in here we're getting back the thermal matrix that we asked for. In this case, it's the inlet air temperature in here. This is part of the computer that it's actually got the measurement from. And if I look at my HMC, I can't see this thing called D1, which I presume is the, that thermal device in the machine that's actually measuring the temperature, allowing the service processor to realise if it's going over its temperature, then it can clock the CPU down, that sort of thing. Okay. And if you've got a big machine, you'll actually get several values back, because particularly the bigger, older machines, they have those intelligent power supplies. Each of those is monitoring its own input temperatures and output temperatures and giving you back different numbers. These are sort of blank in here. This is a repeat in here, and so it looks nicely ambient thermal sensor here. Presumably this is what this the actual device is, if we could look inside the machine. Here we have a timestamp, 2015 is the year, we're in February the 19th, and so this is 18:23, 23 minutes past 6 and 30 seconds. It's saying here the duration that is actually doing this, checking the numbers and saving them every 30 seconds, and here it is. This is the temperature. Fortunately, it's not 2,200, otherwise the metal at the back of the machine would be melting down. This is actually in hundreds, so this is 22 degrees centigrade. Okay, now this came out at the end, and you get about just a fraction under 2 hours worth of data. So if we go back to the previous one, then we can see this was 23 minutes and 30 seconds. This is the 23 minutes in here. Here's the 22 minutes and 30 seconds one. Let's scroll back all the way back in here. We'll see that these actually change. These are inlet temperatures. Oh yeah, now we see this thing here. This is the exhaust temperature value. So that puts all the exhaust temperatures every 30 seconds. So there's 120 values for 2 hours. And then out here we can see the exhaust temperature coming out the back of the machine is 31 degrees centigrade. Okay. So we're doing quite well. We've got the data there. The format is horrible. I've been manipulating the data with some awk scripts and things to try and get it into a sensible ordering so that we can actually graph that data in a minute. Now I'll just drag that back down to here and clear the screen. If I cat a file called Y, similar sort of thing in here. The only thing that's changed now is this thing in here, so we have a power metric value instead. This gives us the wattage going in and out of the machine. Now the nice thing, it actually measures the input and output wattage. The difference between them, of course, was actually the efficiency of the power supply. So you can actually prove that we're, I think using one of those standards, aren't we? Star standard or something, and you can actually check that we have, I think it's above 85% efficiency on our power supply, so we're not wasting a lot of power actually converting the electricity down to the couple of volts that we use inside the machine, which is good, which means your power supplies are not actually getting very hot in themselves. It's the CPUs, the memories and the disks. So if we run that one, again, very simply bash Y, and we'll put that through the less command. Okay. This one takes a little bit longer. This command, the wbem CLI command, is formatting up the crest. It sends it over to the service processor. It has to work out what you want, get the numbers, and then push it back in the right format. And then the command is actually reformatting it here for the screen. So again, we have in here what we've got: average input power here coming in, and the number we have in here at the moment is 426. Okay, and we can see it's failed. If we carry on down here, oh, there we go. We got max input power here. And we'll scan through them again. You won't be able to see this in the movie, but I'll stop it. Yep, it's just the two values then: the max input power and the average input power. Okay. And the rest of it, I think, is similar sort of things. The timestamps are the same. One thing I did notice was that the order of these values come out differently. We've got the metric number up in here, and the timestamp below it now, just to make things really awkward once you've got your scripts working. But never mind. We now have that data, and we can do something with it. Okay, so I took that data and I built a graph using Google Charts. And so here we have our Power 8 machine. This is an S822. We should put an L on the end of that. It's actually running a Power KVM. So I logged onto it and gave it lots and lots of workloads. It has 20 CPUs, so I was running 19 of them flat out. And you can see this is the idle that was